In the name of God, the most gracious, the most merciful, peace be upon you and God's blessings. In this post, we will be looking to solve the problem for block shear for the first case, where block shear reduction coefficient for tension UBS equals 1. There is another case, or the second case, where the block shear reduction coefficient for tension UBS equals 1/2, as we can see in the slide as case B. There are two bolts at the bottom. The shear force acts near the edge. Case B will be discussed later. This is a snapshot of the solved problem quoted from Professor Alan Williams' handbook, for which we are concerned with case A, which is a case that we have a uniform stress for tension coefficient of reduction factor for block shear, or UBS equals 1. In the solved problem, it is required to find the resistance to block shear, where we have a uniform stress distribution for tension force, shown in figure 5.7a. We have a given W section, which is W16 by 40, grade A36. The overall depth is 16 inches. The horizontal and vertical distances from the edge to the column of bolts are equal, and they are 1.5 inches. The vertical spacing between bolts is 3 inches. The bolt diameter is 3/4 inches. We start the solution for the solved problem. We have W16 by 40, which has a web thickness of 0.305 inches. The breadth is 7 inches. A36 grade will give a value for the yield stress equals 36 kSi, and the ultimate stress equals 58 kSi. The height between the upper edge and the third bolt is equal to 7.5 inches. The hole diameter will be equal to the bolt diameter plus 1/8 inches. Since the bolt diameter is 3/4 inches, then the hole diameter will be 7/8 inches. As a reminder, I quote a picture from Professor Segui's handbook. If we have a section subjected to tension, the force in the hatchet portion will follow the direction of the applied tension force. In our case, the shear force acts as a tension force acting downwards. Then the tension force distribution on the lower side will be acting downwards. The shear force also acts downwards. For the hatchet area, the vertical section which is subjected to shear is a vertical section with a height of 7.5 inches and a width equal to 0.305 inches. The lower section, which is acted upon by a tension force, has a length equal to L sub h, which is 1.5 inches. We notice that the vertical section that is subjected to shear passes by 2.5 bolts. The lower section that is subjected to tension passes by 1/2 bolt. The area of the gross area of shear is equal to the vertical distance multiplied by web thickness, or can be written as A sub GV, and can be found as equal to 7.5 by 0.305 equals 2.29 inches square. The net area subjected to shear is termed A sub NV. The area will be equal to the gross area minus the area deducted by the area occupied by holes. Then A sub NV equals 2.29 minus open bracket 2.5 by 7 over 8 by 0.305 equals 1.629 inches square. In the next slide, we can see the case of shear yielding, where we have A sub GV equals 2.288 or approximated to 2.29 inches square. The acting shear stress is equal to 0.6 by F sub Y, F yield. Since F yield equals 36 KSI, the shear stress accordingly will be equal to 0.6 multiplied by 36 equals 21.6 KSI. Multiply the shear stress by the gross area for shear to get the shear yielding, which will be equal to 49.42 kips. For the case of tension rupture, first estimate the gross area for tension, which is equal to the length 1.5 inches multiplied by width thickness, or 1.5 multiplied by 0.305 equals 0.458 inches square. To get the value of the net area for tension, which we call A sub NG, we will deduct 1/2 hole diameter area. As we can see from the slide, the ANT will be equal to 0.3241. The UBS value equals 1. The ultimate stress, F ultimate, equals 258 KSI. For the next slide, we have the case of shear rupture. The gross area for shear, or AGV, equals 2.288 inches square. The net area of shear ANV equals 1.621. The acting shear stress is equal to 0.6 by F alt. Since F ultimate equals to 58 KSI, the shear stress accordingly will be equal to 0.6 multiplied by 58 equals 34.8 KSI. Multiply the shear stress by the net area for shear to get the shear rupture, which will be equal to 56.411 kips. The value of shear rupture is bigger than the value of shear yielding. The case of tension rupture is repeated since it is common. Now we are ready to proceed to our estimation for block shear. We have yield stress of 36 KSI and ultimate stress of 58 KSI. The gross area for shear AGV equals to 2.288 inches square. The net area for shear ANV equals 1.621 inches square, and the net area for tension is equal to 0.3241 inches square. The first case is the case of shear yielding and tension rupture. For that case, the shear stress is equal to 0.6 F yield, while the tension stress is F ultimate acting on the net area of tension. Please refer to the left side of the slide. Shear yielding estimated as equal to 49.42 kips. The tension rupture equals UBS by F alt by ANT. The UBS value equals 1. ANT equals 0.3241 inches square, and the F ultimate is 58 KSI. The total value of tension rupture will be equal to 18.798 kips. Adding the value of shear yielding and tension rupture will give a total value of 68.218 kips. The value of shear yielding and tension rupture, we call it R sub N1. The second case is the case of shear rupture and tension rupture. Please refer to the right side of the slide. For that case, the shear stress is equal to 0.6 by F ultimate, while the tension stress is F ultimate acting on the net area of tension A sub NT. The shear rupture value equals 56.411 kips, and the tensile rupture equals 18.798 kips. Adding the value of shear rupture and tension rupture will give a total value of 75.028 kips. The value of shear rupture and tension rupture we call R sub N2. If we want to find the LRFD value for block shear, for the first case we multiply phi, which is equal to 0.75. Please refer to the left side of the slide. Phi will be multiplied by opening bracket 0.6 F yield by AGV plus F ultimate by UBS by ANT. The final LRFD value for case 1 equals 51.16 kips. While for the second case, please refer to the right side of the slide. We will multiply phi by 0.6 F alt by ANV plus 0.6 F alt by ANT by UBS. The final value for case 2 will be equal to 56.41 kips. We will select the minimum value of the two values, which are 51.2 and 56.46. The final LRFD value will be equal to 51.20 kips. That means shear yielding and tension rupture controls. For the ASD value, consider 1 over omega equals 1 over 2, multiply 1 over omega by R sub N1, which is the value of shear yielding and tension rupture. Also multiply 1 over omega by R sub N2, which is the value of shear rupture and tension rupture. Select the minimum value of the two cases, which will be the case of shear yielding and tension rupture. We can find that the final ASD value for block shear will be equal to 34.13 kips. We have come to the end of the solved problem. Thanks a lot and see you.